Hi, I'm Upali Sirivodin. I'm going to get you ready for test 3 on chapter 6, 7 and 8. Today I'm going to go through chapter 6 material in the PowerPoint presentation. The chapter 6 is on energy changes, reaction rates and equilibrium. There are 3 sections. First, energy. Energy is important part of we need to know more about energy changes and how they come from chemical reactions. We need to draw energy diagrams to explain exothermic and endothermic reactions. The second part is reaction rates. Reaction rates are important. The second part is reaction rates. Reaction rates are important to carry out reaction at a reasonable rate. There are several factors that affect reaction rates: concentration, temperature, and catalyst. So equilibrium is very important because a lot of reactions are at equilibrium, which means they take place towards the reactants going to products and products turning back onto reactants. The rates of the reactions, coexistence of reactants and product. So we need to know how to change this equilibrium to get what we want. The changes that we can make are based on Le Chatelier's principle that we're going to look into. So we will Le Chatelier's principle that we're going to look into. So we will use the equilibrium principles to know how the body temperature is maintained in humans. So we're going to define energy and calories, joules, kilocalories, dietary calories. We're going to use bond dissociation energy to predict bond strength. We're going to use energy changes in reaction and classify reactions as endothermic and draw energy diagram with potential energies of reactants, products, and activation barrier. Then we're going to predict the effect of concentration, temperature, and catalyst on the rate, concentration, temperature, and catalyst on the rate of a reaction. Then we're going to describe the basic features of chemical equilibrium and write equilibrium expression for reactions and define equilibrium constant. And then we're going to when equilibrium is disturbed, which way the reaction would go, forward or backward direction. So we will use this principle to explain the rates, to explain the regulations, to explain the regulation of body temperature. There are many forms of energy. The total energy is potential energy and kinetic energy. So they are most common energy forms, potential energy and kinetic energy. So potential energy could be macroscopic or microscopic, just like potential energy of and potential energy of large objects, or kinetic energy of large object, macroscopic. Energy is the capacity to do work. Potential energy is considered as stored energy due to position of the component energy stored in the bonds. Kinetic energy is due to motion, energy possessed by a molecule or system due to motion. For energy changes, law of conservation of energy applies. Law of conservation of energy applies. it states that total energy of a system does not change. Energy cannot be neither created nor destroyed. If you look at the diagram, you do take a ride, the various amount of potential and kinetic energy conversions. At the bottom of the ride, in the middle, lowest point, the kinetic energy is highest and the potential energy is lowest. As the kinetic and the potential energy is lowest. As the kinetic energy gets lower at the point where the highest point is, there are a lot of potential energy, but the motion is, there's no kinetic energy. Kinetic energy is measured by half mass times velocity squared. That's the definition of kinetic energy. Kinetic energy of molecules are proportional to Kelvin temperature. As energy-wise, potential energy has higher energy and unfavorable or unstable, so that they can lose the energy and become lower potential energy. Lower potential energy is a favorable situation. This R refers to reactants, P refers to products. Products with higher potential energy is favorable. Potential energy is stored in energy, exists in natural attraction and repulsion in bonds, bond formation process. Bonds are holding atoms together. Potential energy possessed by chemical, stored in chemical bonds. Breaking bonds require energy. Forming bond release energy. So this principle is going to be used to calculate enthalpy of a reaction or bond dissociation. Enthalpy of a reaction or bond dissociation energies. Units of energy are important. Calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Energy is joules. Calories are mainly used for heat. General form of energy unit is joules. Joules apply to many things. 1 calorie is equal to 4.184 joules. Calorie is equal to 4.184 joules. Both joules and calories can be reported in larger units, in kilojoules or kilocalories. 1,000 joules is equal to 1 kilojoules. 1,000 calories is equal to 1 kilocalorie is equal to 4.84 kilojoules. So we use conversion factors to convert energy from different unit to another. A gummy bear is 9 calories. How much energy stores a bear in joules? So we use 9 calories per gummy bear. Conversion factors and cal. So we convert dietary calories. So nutrition and calories are different. They are equal to kcals, 9 kcals, 9 kcals. So really 9,000 calories are in a gummy bear, real calories. Then when you convert that 9,000 real calories through the conversion factor, we get 37,660 joules, 66 joules. We use factor label method to conversions. as shown here. Talking about bonds, where the potential energy of molecules are stored. Breaking bonds requires energy because bonds hold atoms together. Forming bonds release energy. When they are formed, the energy is released. So it requires release. So it requires energy to break bonds. Making bond release energy. To cleave a bond, chlorine-chlorine bond, 58 kilojoules per mole must be added. That is possible. To form a bond between chlorine-chlorine atoms, 58 kilocalories per mole is released, is negative energy. Delta H enthalpy is the heat of reaction or enthalpy change. Talking about enthalpy change, heat release or absorbed during the bond making and bond breaking process. The bond dissociation energy is the delta H for breaking covalent bond equally between the electron between the two atoms. So these radicals are formed, breaking hydrogen-hydrogen bond that require 104 kcals per mole. So the same amount of energy is released. Enthalpy of reaction is for bond making is exothermic. Delta H exothermic. Delta H is equal to minus 104 kcals per mole. The stronger the bond, higher the bond dissociation energy. There are bond dissociation energy tables you can look into in the appendix book of various bond energies. The hydrogen fluorine bond in hydrogen fluoride is 136 kcal per mole. HCl bond is 103 kcal mole. Bond is 103 kcal mole. So bond energies are not equal. Some bonds have high energy. That means it's difficult to break. Relative shows the relative strength of the bonds broken or formed in the reaction. Delta H negative is exothermic reaction. That means you compare delta H of bond making and bond breaking during the reaction. Delta H of bond making and bond breaking during the reaction. Bonds are broken in the reactants. Bonds are formed in the products. So reaction is exothermic. More energy is required to break the bonds than form the reactants. Products have stronger bonds. When reactants have stronger bonds, the overall energy is absorbed. Less energy required to break the product from the road. Products have weaker bonds. So therefore, products have weaker bonds. So therefore, exothermic reaction. It's summarized in the table is the exothermic and endothermic and exothermic reactions. Endothermic broken in the reactants are stronger than the bonds formed in the product. The products are higher in energy than the reactants. Exothermic reaction, heat is released. Delta H is negative. The bonds formed is released. Delta H is negative. The bonds formed in the products are stronger than the bonds broken in the reactants. The products are lower energy than reactants. So we draw energy, potential energy or energies of reactants relative to products and transition state. For a reaction to occur, two molecules must collide with enough kinetic energy to break bonds. When the two reactant molecules state, where it's neither reactants or products, that's a changing reactants to products. Instead of changing reactants to products is called transition state. How molecule collide, the orientation of two molecules must be correct. So correct orientation only leads to correct product. So this is explained in the diagram here. See, with right orientation, they collide and go to transition state where the bonds between A and B are breaking and bonds between B and C are formed. So this is the minimum energy. So this is the minimum energy, activation energy that's required to go through the transition state. That's called transition state energy barrier. So that barrier should be passed before reactants can go to products. I assume to be lower energy than the reactant because the energies of reactants are higher than the products. So it's an exothermic reaction. The energy is released when reactants go to product. Release, so this is energy neutral. Activation energy, E sub A, the energy of activation is the difference in energy between the reactants and the transition state. It can be thought of as an energy barrier that must be overcome for the reaction to occur. Thought of as an energy barrier that must be overcome for the reaction to occur. So this is the characteristic of energy diagram. So we can compare different energy diagrams for exothermic and endothermic reaction. First one is exothermic, lower energy than the reactants. The second one is the endothermic reaction. Products have higher energy than the reactants. Still, they must go through activation energy. So first reaction has low activation and the second, first reaction has low activation and the second one has higher activation energy. When reaction has high activation energy, that's difficult to take place. So this table reaction. So reactants have same energy, potential energy increase as the bond breaks, go into transition state. So for the endothermic reaction, products have higher potential energy. Therefore, heat is absorbed going from reactants to products. On the second reaction, exothermic reaction, reactants have higher products, therefore energy is released. So it's summarized on the right side, endothermic products have weaker bonds and higher energy than reactants. Energy is absorbed. Heat of reaction for the endothermic reaction, energy is released, as well as heat of reaction is released. So that's how you interpret energy diagrams. Splitting water is very important for producing hydrogen to fuel our hydrogen fuel cells using hydrogen. So hydrogen is obtained by splitting water into oxygen. There's an activation barrier, and that's an endothermic reaction. That energy is provided by electric power. So normally minimum of 1.23 volts to split water. However, at this voltage, the potential energy needs to be at least 3.0 volts to utilize the full spectrum of light. So infrared only won't do the work. This is the photo splitting of the work. This is the photo splitting of water using sunlight. So this is being studied right now for the production of hydrogen from water. Now we're going to talk about rates of reactions. There are several factors that increase the rate of reaction. Increase in the increase in the concentration of reactants have the effect of increasing number of collision and increase in the rate. Concentration always increase the rate of reaction. Increase in temperature of a reaction increase the kinetic energy of molecule, increase the reaction rate because a lot of molecules can pass through the activation barrier. A catalyst is a substance that up reaction rates. After the reaction is complete, they are not changed. We can recover them unchanged. Catalysts lower the activation energy, so provide lower temperature to allows lower temperature to with reasonable reaction rate. The effect of catalyst is shown in this diagram. The activation energy of catalyzed graph is lower. Therefore, reaction takes place at lower temperature. Catalysts only make reaction go faster, but heat of reaction is still the same. Heat of reaction is same for the both activation energy and make it go faster. One of the enzymes that we use in photosynthesis called photosynthesis system 2 is an enzyme that catalyzes oxidation reduction of plastoquinone from water, hydrogen from water. This is water's leading step in the photosynthesis. Photoquinone, reduced photoquinone combined with carbon dioxide to produce hydrocarbon use of catalyst to biological catalysts that use to do reaction in cellular level. Now coming to equilibrium. A reversible reaction can take place in either direction. Equilibrium is a situation where reactant going to products going to reactants. Forward reaction is reactants to product proceed to the right. Reverse reaction is the one that proceeds to left. Products to reactants. In the equilibrium reaction, both take place at same. In the equilibrium reaction, both take place at same or different rates. The system is at equilibrium when the rate of the reaction of the forward reaction equals rate of the reaction of reverse reaction. The net concentration of reactant and products equilibrium. Once the rates of forward and backward reaction are equal. Reactants and product concentration remain at the same at the equilibrium. That concentration is called equilibrium concentration. Concentration, we can define an equilibrium constant for particular reaction. Equilibrium constant is K. K is defined as concentration of products divided by concentration of reactants multiplied by their stoichiometric to the reactants multiplied by their stoichiometric to the power of their stoichiometric coefficient. C to the power small c, d to the power small d divided by a to the power small a, b to the power gives the equilibrium constant value. If you plug in equilibrium concentration, you get the equilibrium constant. The square bracket with the product or reactants is the concentration expressed in bracket C is moles of C at the equilibrium. So to explain more about equilibrium constant for the reaction of nitrogen, plus oxygen going to nitrogen oxide, monoxide. You write the equilibrium constant. Products on the top, NO concentration to the power of stoichiometric divided by nitrogen concentration. The stoichiometric coefficient is 1 on both nitrogen and oxygen, therefore to the power 1. The coefficients become the exponent. The value of K, the equilibrium condition. If K is greater than 1, equilibrium favors products. Concentration of the reactants are small. Equilibrium lies to the right towards product side. Equilibrium constant is less than 1, product side. Equilibrium constant is less than 1, equilibrium favors reactants. Equilibrium lies to the left, product reactant side. If equilibrium constant is close to 1, both reactants and products are present in to a significant concentration. How to calculate the equilibrium constant? Write the equilibrium expression. A2, B2 going to 2, AB. AB. Equilibrium constant is AB power 2, A2 times B2 concentration. Step 2, substitute the given concentration in the equilibrium expression. Calculate the K. You need to do an experiment to calculate or it will be given. So in this case, AB2 concentration is 0.50 and A2 and B2 is 0.25. So from the wording of the problem, you can figure that out. So when you calculate the equilibrium constant for reaction is 4.0. It's much larger than equilibrium concentration, larger than 1. So therefore, product favored. Most of the reactants are go on and large amount of products out at the equilibrium. We use Le-Chatelier principle to change the equilibrium position to obtain what we desire. Equilibrium is disturbed or stress. The system will react in a direction that counteract the disturbance or relieve the stress. This is the Le-Chatelier principle. Concentration system will in a way react to remove the concentration or add concentration of the to counteract the changes. If you increase the temperature of the equilibrium, depending on whether exothermic or endothermic reaction, depending on whether exothermic or endothermic reaction will shift towards the side to counteract the temperature increase. Pressure changes are cause system to go towards the direction where number change. If the pressure is increased, the system will change to a direction where the number of particles will decrease. To summarize Le Chatelet principle, we have put our conclusion in the table. Effect of changes in condition on equilibrium. Add in reactants, equilibrium will favors the products. If you add products to remove reactants, removing reactants, the more reactants will be formed. Products will react to form more reactants. Removing will add. Adding will remove. Adding product, remove. Adding product, equilibrium favors the reactants, and removing products, equilibrium favor the products. It will go to the product side. The temperature, increase in temperature, that means it try to remove the temperature, increase in temperature. And the exothermic reaction, other way around, equilibrium favors the reactants, goes to the reactant side. Decrease in the temperature has opposite effect. Decrease in the temperature has opposite effect. Endothermic reaction, equilibrium favors the reactants, and in an exothermic reaction, equilibrium favors the products. Increase in pressure, equilibrium favors the side that has fewer molecules. Increase in the pressure, equilibrium favors the side that has more molecules. So this is in summary about the equilibrium applying Le Chatelet principle to the changing conditions on the equilibrium. Chapter 7 next time, and will be put in the Zoom meeting under chapter 7. Take care.